Hello, I'll start on relativistic dynamics. What I'm going to do is, I'm going to first show that under the Lorentz transformation, momentum is actually not conserved. Then I'll explain how Einstein came to the rescue and saved momentum conservation. And after that, how that lead on to the formula for E is equal to mc squared. Now that's just an imaginary line. Let's start by thinking of two colliding bodies. I have one ball here and one ball there, and they come to each other. So these are perfectly elastic balls. When they collide, they bounce off without any loss of kinetic energy. So in this case, I choose a direction so that when they bounce off symmetrically, in a symmetrical direction. So that the paths for each ball are symmetrical to each other, meaning that those angles are equal. Right, that's my x direction. So this is my line of symmetry. Okay, so that's my starting situation, and you can imagine that this is a particular frame of reference, and an observer at rest in this frame, this is what they see. I'll need some names, so call that ball A, and that one B. So that's a perfectly possible situation, as we would understand from Newtonian mechanics. Next, suppose that I now change my frame of reference. I'm going to change to a frame of reference that moves to the left. Alright, as this ball goes up and bounces down, I'm going to change to a frame of reference which moves with this ball. Alright, the frame of reference that moves with this ball so that the x position of the ball is always the same, and that ball just goes up and down in that frame of reference. So if I move at a velocity that is the same as the horizontal velocity of this ball. Now that other ball, of course, will still do this, but as I move this way, this ball will move faster in the x direction. So that again is perfectly possible. So let me change my frame of reference to one in which I shall use x for that. Of course, I'm going to use x for this, right? That one, and okay, so that's my so in this frame of reference, right, this ball A will be moving up, and that ball B, it will be moving to the right more quickly, but of course they will still collide. B will still bounce off, and A will come back vertically downwards after colliding. Now let this velocity be v naught, this upward velocity. Right. Now, what we want to do now is to is to look at the momentum. Look at the momentum of this, or of the two balls before and after collision to check if they are the same. Because from what we understand from Newtonian mechanics, that momentum is conserved. The momentum, the total momentum should be the same before and after collision. So let's write down the momentum for the balls. Now we'll be looking at just the vertical momentum. Alright, so let me clean this away. Ball A and ball B. Okay. Before collision, let's look at the momentum. The mass, let the mass of the ball be m. Okay, same mass because identical balls. So the vertical momentum of A is m times v naught. Okay. What about the vertical momentum of B? Now let's think about this a little bit. What I have here is a frame of reference that I got when I started moving to the left with the ball A, so that I'm in the frame of reference where A would move up and down vertically. Now, but I can equally well have chosen another frame of reference in which I moved with B, so that it is B that would be moving vertically down and up, and A would be moving at an angle. And that's possible because we have a symmetrical situation. So if I'm in the moving frame of B, I would expect that B would have the same speed v0. Okay, since it's completely symmetrical. So in that moving frame for B, we have the velocity v0. Now, what we know from time dilation is that as far as A is concerned, an observer in this frame, this moving frame, this particular frame for A, when that observer look at the ball in the moving frame of that moves in the frame of B, the observer will see that there is time dilation in the frame that moves with B. All right. Now, if there is time dilation, that means that things slow down. So in the frame of B, in the frame that moves with B, the velocity of the ball will be v0. But in the frame that in the frame that moves with A, an observer there would think that the ball in B's frame would be moving more slowly. Now, slowly by how much? So v0 would be the velocity of the ball in the frame that moves with B. It will be slower by b0 over gamma. Because that's the factor that the time slows down by. So the velocity will slow down by the same factor. So now, back in the moving frame of A, the vertical component of B, as it comes down here, would therefore be slower, be v0 over gamma. And the corresponding vertical momentum of B is then m times v0 over omega. And because the vertical momentum is downwards, so we have a minus sign. Right, that's where we are now. Now let's look at what happens after collision. After collision, ball A moves back down at the same velocity. So momentum is again mv0, but with a minus sign because the direction has changed. What about B? B bounces up, it's completely symmetrical, so we expect the same momentum but a change in sign. mv0 over omega. Right? So then we have all that we need to find the total momentum. So let's find the total momentum. Right. Now total momentum just means that we add them together. We have to do it before the collision first. So when we add those two together, see, let me simplify as I add. There are common factors m and v0. So I can take that out of a bracket, and in the bracket I would have 1 from there and minus 1 over omega from here. Right. Now likewise, I have for the after collision, the total momentum is m0 mv0 bracket. Now this time I have a minus sign there and a plus sign there. What I'll do is I'll take out a minus. Alright, so that gives a 1 here, and for that I would have a minus 1 omega. So I'm doing this because then I can compare the two terms directly in the bracket. Now if you look at this, you see that the two expressions, the total momenta are the same before and after collision, except for the sign. So the sign has changed. Now, you know, for momentum, directions are important, not just the magnitude. So when we say momentum must be the same, we mean both the direction and the magnitude. So therefore, if the direction is now different, it means that the momentum is different. And so we now have a situation where momentum is not conserved. Now that is a big problem because the conservation of momentum is important for in classical mechanics. So, and because momentum is not conserved, it means that the classical mechanics doesn't work anymore, or that all these things that we've talked about, about Lorentz transformation and about how light speed is the same in all frames of reference, this must be nonsense. Now, this is a point where Einstein came to the rescue. Right, in order to insist that both that momentum must be conserved and that Lorentz transformation and the constant light speed is still correct, the thing to do is to look at the mass there, look at this momentum here, right? We are saying that because B is moving to the right, this motion, as a result of this motion, the mass of B, right, let me start again. What we have seen is that in this term for B is that the velocity of B is slower because of the time dilation, right? That's why you have the over gamma down here. Now the idea is to think of this as because the mass has increased. Alright, to think that it has slowed down, not right, to instead of thinking of it as a time dilation, we could also think about it could also slow down if it is because the mass has increased. Now suppose that the mass of B has increased also by the same Lorentz factor. Then when you divide the new mass by Lorentz factor, you would get back the same mass as before, and we can see that it is then possible to get the same magnitude of momentum as A. So let's try that out. The idea is that we are thinking that thinking in terms of the velocity slowing down because of the mass increase. So we're saying that as far as B is concerned, the mass has increased by a factor of gamma. Alright? Now if that's the case, let's see what happens. We would have an additional factor of gamma there, and an additional factor of gamma there. Then this gamma and this gamma will cancel. And then you have just minus mv0 there and mv0 there. So this time, when we find the total momentum, you have mv0 minus mv0 is 0. And minus mv0 plus mv0 is 0. And 0 is equal to 0. So the total momentum before collision is now equal to the total momentum after collision. And so Einstein has rescued momentum conservation. So finally, we have to insist that the total momentum must be conserved. It leads to the result that mass must increase. And it must increase by exactly this factor, the Lorentz factor times the mass that was the mass that was at rest. Right. Okay. Now at this point, let's take a closer look at this. For convenience, in later calculations, I may make use of this symbol where m0 means the mass that the body has at rest, or what is often called the rest mass. So I'll use m0 with the subscript 0 to indicate that it's a rest mass, and m to represent what we call the relativistic mass. That means the mass as a result of the movement. That would be the Lorentz factor times the rest mass. Now if we write out the Lorentz factor in full, this is what it looks like. The square root of 1 minus v squared over c squared. Now if you recall, if you look at this, you see that v squared over c squared must be a positive number. Okay, so 1 minus a positive number must be smaller than 1. So that's why we end up with a smaller number in the denominator, and when we divide, we have a bigger answer. Now, but if you look more closely at this expression, this is v over c, the velocity of the moving frame, divided by the speed of light. Now, what if the body moves at a speed that is more than the speed of light? You see that you have a number that is more than c divided by c, and the answer must be more than 1. And you end up with 1 minus something which is more than 1, and you get a negative answer. And what happens when we take the square root of a negative number? You get an imaginary result. So that seems to show that there is something that we don't understand, alright, about an object going faster than the speed of light. Next, let's think about what happens if we start from a small value of v and we slowly increase that towards the speed of light. Now if you do that, then v over c will get closer and closer to 1 from a small value. So 1 minus 1 will become closer and closer to 0. So, which means that the rest mass divided by this square root will become larger and larger. So it would seem that as v tends towards c, this relativistic mass will tend to infinity. Now that seems to suggest, if this is true physically, it would seem to suggest that nothing, at least nothing that has a mass, can move faster than the speed of light. Right. The next thing that I'm going to do is to derive an expression for the kinetic energy of a particle, the relativistic kinetic energy. Now, in classical mechanics, we know how to derive the kinetic energy. That is half mv squared. The way to derive half mv squared is to say that, right, I have a body with a mass m, and then I have a force on the body, and this is either in free space or on a frictionless table, so the body can move without any resistance. So the velocity increases from 0 to a certain value v. And the way to do it is to calculate the total work that is done, and in terms of the mass and the velocity, and the result that we would get is half mv squared. So that's how it's done in classical mechanics. So we'll follow the same idea, and we would expect that there should be difference in when we're using this Lorentz transformation and when you have all these time dilations and mass increase. So we will not expect that you will still end up with half mv squared, but we can use the same idea. It means that we can start by finding the work done on the body and see what we get. Now, in order to do this, along the way, we need to use Newton's second law. So that's what we have to think about first. Now, Newton's second law is force times the rate of change, or is force is equal to the rate of change of momentum, P. Now, momentum is equal to mass times velocity. But in what we have seen, the mass increases with velocity. So if m0 is the mass at rest, then when it's moving, the mass would be gamma times m0. So now we have the relativistic form of the Newton's second law. It picks up this Lorentz factor. So that's what we have to use. So let's start. I'll call Ek the kinetic energy, and if there's no friction and the body just accelerates under the force, all the work done by the force must be converted into kinetic energy. There's nothing dissipated by heat or used to do work against any potential. So just free space or frictionless table. So this must be equal to the work done by the force, and the work done by the force must be equal to force times distance, right? Integrated over the distance of the motion. So what we then need to do now is to start substituting expressions for F and distance, and eventually try to integrate the expression to see what we get. See, so this is the same as integrating F I'm going to do some algebra here. There's a dx there. I'm going to insert a dt there and a dt there. The purpose is to make use, to rearrange it in a form that I can make use of expressions like that. Right. Okay, so then the f here would be dp by dt. The dx dt there is velocity v, and I still have the dt there. Okay. Now I can cancel the dt and I'll get v dp. Right. And with v dp I can integrate by parts. Now, right, okay. So I'll have v and p minus, so v dp becomes p dv. Okay. Now at this point we need to think about the limits. So there's a bar that we need to draw there. Okay. Now let's think about the motion. I'm interested in just finding purely the kinetic energy, so I will start the motion, the body at rest. Okay, so at first there's no kinetic energy, then I'll start applying this force F. So in the beginning, the velocity is 0, and then after some time it will gain a certain velocity v. So these will be our limits. Alright. Now since we're actually going to do this integration, we need to be a bit more careful about the variables. So the v there is the final velocity after a certain time, but the v in there from the integrand should be a dummy variable that we integrate over. So I'm going to put a prime over those. So this is what it looks like. Okay, let's carry on. Now we can evaluate this part. When v prime is 0, that's just 0. When v prime is v, when it reaches the final velocity, we just plug the v into there, and the p there just means that it must be the corresponding velocity. So let me write that out. Vp. And what do we mean by corresponding velocity for p? Right. If you look back at this expression there, p is actually gamma m0 v. Now m0 is a constant, but we see here that p depends on v. So that v there must be the final velocity for the p here, the momentum here. But the gamma also contains v. That's Lorentz factor is also a function of v. So it just means that for this p, it would be actually gamma m0 v using the final v. So let me use that instead. So v times gamma m0 v. So that's my momentum at the final velocity. And likewise, for the integral, the p there would be gamma m0 v. But it will be v prime, because I'm using v prime as the variable in the integral, dv prime. So here's what we have. Now let's try and integrate this. So there's a v there and a v there, so this is gamma m naught v squared. And you can write out the Lorentz factor in full. This gives m naught v prime over square root 1 minus v prime squared over c squared v prime. And we get an expression here that we can actually integrate. Let's see what we get. That's my EK, right? That's where we are. So let's try and integrate this. EK. Gamma m naught v squared minus m naught Let's see if that's correct. I have an m naught there and an m naught there. What happens if I differentiate this? If I differentiate this, I have a power of half there, which has to come down. So it gains a factor of half. But I would need to differentiate the term inside the square root. That gives me a 2 v prime factor. So that's the v prime, and the 2 from the power will cancel with the half from the square root. And I would have an additional c squared to worry about. Right, to remove that I need to insert a c squared factor there. And then I have a minus sign to get rid of, so I have a minus sign outside that to take care of it. Right, so when we integrate this, we would get that. You can check that simply by differentiating this to make sure that you recover this expression. So this is it. Let me just run through the steps. This is m. Right, the next step, what we need to do, so write this out, like that, and here we need to plug that into there. Minus and minus becomes a plus. So m naught c squared square root of 1 minus v squared over c squared. So the v there is substituted into the v prime here to give a v there, and minus sign there, and the 0 goes into the v prime there, that becomes 1, and this gives m naught c squared. And now we have a bit of algebra to do down here. Alright, and if you combine the two fractions, you will find m naught c squared over square root of 1 minus v squared over c. Right, I'll leave you to try that out. Now, but that is just the Lorentz factor again. So I have gamma m naught c squared for this and minus the m naught c squared. Now if you remember, gamma m naught c squared is just the new mass of the body moving at a velocity. That was how we interpreted it. And the m naught here is the rest mass of the body. So as the body moves, it becomes heavier because of this gamma m naught. Now, and we have an interesting result. We have the result that the kinetic energy is equal to this. It's equal to the relativistic mass, the moving mass times c squared minus the rest mass times c squared. Now, it is as if when the object is moving, it becomes heavier. And then you have this equation that looks like it relates this increase in the mass to the energy. So this seems to suggest that the mass increase, first to suggest that the increase in mass is because of the energy. But if you let your imagination run on a bit, it also seems to suggest that maybe, just maybe, the kinetic energy has mass, which is why the mass increase. Now, if that is the case, we can then go on to further think about what if somehow the mass at rest, when it is not moving, it has a mass. Could it be that this mass of the object, when it is just sitting there, could it somehow be converted into energy? If it can be converted into energy, then perhaps you would actually get E is equal to m naught c squared. That would actually be the amount of energy that you would get. Perhaps the mass of the object is actually just energy which is somehow condensed into a solid object. So there is a lot of imaginations and maybes and what if down here. But it is this kind of ideas that eventually led on to this formula to Einstein to suggest that E is equal to mc squared. So at the time that he did this, if you look at the history, it was about 1905. It was well before the time when E is equal to mc squared was first demonstrated dramatically by the atomic bomb at the end of the Second World War in 1945. So it was all theories and maybes at the time that Einstein published this result. And later on it becomes amply verified in the atomic bomb and in nuclear energy and in lots of other types of experiments. So this is how E is equal to mc squared is derived. Right, the next thing I'm going to look at is something called four vectors and an idea called Lorentz invariance. Now this is part of a way to arrange the Lorentz equations and a way to look at or arrange the mathematics of like the Newton's second law and the momentum equations, so that it is easier to do calculations in relativistic dynamics. Because we know how to do calculations in classical mechanics with Newton's second laws, momentum conservation, acceleration equations and so on. But in special relativity, there is this additional factor of gamma, of the Lorentz factor that causes the mass increase, and the equation of motion becomes more complicated because of the appearance of this Lorentz factor in the Lorentz transformation that relates coordinates at different frames of reference. So calculations do tend to get quite lead to quite complicated algebra if you're not careful. And that's where the idea of 4 vectors come in. It's a way of organizing the equations so that hopefully it becomes easier for calculations. And eventually we are going to look at a problem which uses this idea where we collide 2 particles in different and have to calculate the energy that you need in different frames of reference. Now the idea of 4 vectors is tends to be quite abstract if we go straight into it. So I'll try to motivate the idea by going back to the Lorentz transformation equations and start rearranging it from there. That's one. Now, the other one is the time. Okay, that's the time. And we have also have 2 equations for the x and z coordinates, for the y and the z coordinates. Now this we have not looked at just now, but the idea is that since these coordinates are perpendicular to the direction of motion, I assume that if the frame is moving this way, then this is the x-axis. But for coordinates perpendicular to it, if I have an object here, then if you change the frame of reference, the object is still at the same height, the same y value from the axis. So the y is the same in either frame of reference. Likewise for the z, which is in the perpendicular direction. Okay, so those 2 don't change. So these are my Lorentz transformation equations. Now, right. So the first thing that we're going to do is to multiply that one by c. Now it's the first step to try to simplify things, although it's not very clear how this is going to simplify. If I multiply that by c, this is what we get, right? So one of the c squared becomes a c when we multiply by c. So that's that. Now the other thing I'm going to do is, because you will see v over c a lot in both here and in the Lorentz vector, let's give it a name. Let's call it beta. So beta is equal to v over c. That's a frequently used notation. So that becomes beta, right? Now I would want those in terms of beta as well. So what I'll do is I would multiply that by the t by c, because I'm going to think of ct together as a coordinate, and that is Well, and that perhaps is convenient because CT has the same units as X. Both would be in, say, meters. Alright? So I would, instead of T, I'm going to talk about CT, and then I have to divide that by C to make sure that I've not changed the equation. And if I do that, then V over C is beta. So that becomes beta. This becomes beta times CT. That's my CT. Okay. So these are the new symbols that we're going to use. Now in the next step, we're going to write this in as a matrix equation. So let's see what it looks like. The coordinates would be those: CT prime x prime y prime z prime, and that would be the unprimed ones: CT x y z. And in the matrix, we could simply read out the terms from there. I'll start from the easiest. The last two do not change, so it's just 1 and 1. Alright, and here we have a gamma from there for the CT, and we have a minus beta gamma for the x. Here I have a minus beta gamma for the CT and a gamma for the x. So those are the non-zero terms. All the rest are zeros. So 0, 0, 0, 0. That's a bit off. 1 there and a 1 there. There. So that's my matrix equation for the Lorentz transformation. Don't clear this. Now the next step, the next 1 or 2 steps might look a little bit strange because it's not clear why we are doing this immediately. But let me just say that just for fun, just for exercise, let me take the transpose of this. Right, so if I take the transpose of this, that one, the column vector becomes a row vector. Alright, and those two matrices become swapped around and transposed. So that on the right is now a row vector on the left. And the matrix becomes flipped over. Now, if you look along the diagonal, the matrix is symmetrical. So the transpose is just the same. There. I shall not bother about writing the zeros. So that's what you get if you take the transpose. the next thing that I'm going to do is I'm going to say, right, if you look at this matrix, you see the minus sign there. Alright, the minus sign there. Now if you think about this matrix, it is to transform from the coordinates from one frame to another frame that is moving, say, to the right, moving with a velocity v, which is inside beta. Beta is v over c. Alright. Now imagine what happens if I reverse the signs of the velocity. So that means instead of transforming from this frame to the moving frame, what if I transform from the moving frame back to the first frame? Then relative to the moving frame, the first frame would be moving in the opposite direction. So that means that I would have to change the signs of the velocity. Alright. Now if I change the signs of the velocity, what does that mean? What does that mean to the matrix? Well, it means that I'm doing the opposite transformation. So it means that if I change the sign, I have to get the inverse matrix to this. You can try that out and check that when you multiply a matrix with positive signs there by this one, you should get back the identity matrix. So for now, let me just use this physical reason as enough to tell us that this is the inverse matrix. So at the moment, I'm still messing about with the algebra and trying to find some way forward, if you like. Right, so there's that. Now, but if, again, I'm still playing with the algebra, if I'm going to change the signs of this, then clearly the right hand side of this equation is no longer equal to the left hand side. But it turns out that if I also add a minus sign there to the CT and there to the CT prime, then the left and right side becomes equal again, because the minus sign there, when I multiply this vector by the matrix, alright, when you look at the original Lorentz transformation equations, would lead to the correct minus CT prime and x prime down here. So again, I'll leave it to you as an exercise if you like to prove that. But the idea is that if you change the sign of those two and change the sign of the minus CT, you will end up with this vector with a minus CT prime. Alright, and that when you expand the whole lot out, it still agrees with the Lorentz equations. So here's where we are at the moment. Now it is at this step that we should try and make sense of this equation to see how we can use it for. So coming back to this matrix, as I've said, this, because I've reversed the velocity, this transformation matrix should be the inverse of that matrix. So the next thing to try is to do what we would do with inverse matrices. When you multiply two matrices that are inverses of each other, you get the identity matrix. So I'm going to do this. I'm going to take this and multiply it by that. I'm going to allow the two inverse matrices to come together and then turn into the identity matrix. Right. But before I do that, I want to make things a bit more, hopefully whatever I'm going to get a bit more general. I'm going to use different, I'm going to think about having different x, y, z, t for this equation and for this equation. Because since this equation refers to general coordinates of in each frame, x, y, z and t can take any values within a particular frame. So let me just call this, rename this as x1, y1, z1 and t1, and let me think of those as, say, a different coordinate in the corresponding frame. So x2, y2, z2, t2, and likewise for the prime coordinates. Okay, so it's still true, just different values of the coordinates. So now, let me multiply the two. Okay, it's going to be right. It will be it will take quite a few minutes if I have to write everything out. But let me just say what I'm going to do again. You have this equation here. All right. On the right side, you have matrix times vector. Okay. On the left side here, you have again vector times matrix. So what I'm going to do is I'm going to take the right hand side of this equation and I'm going to multiply it by that one, but by the right hand side of this equation. Now in matrix multiplication, we have to talk about which side we multiply. So I'm going to multiply the left side of this equation by this. So I'm going to take this and I'm going to multiply from this side. So if I take this and multiply from this side, then this matrix will cancel with this matrix, in the sense that it will produce the identity matrix. So this matrix times this matrix gives the identity. So in effect they cancel, and I'll be left with this row vector multiplied by that column vector. So I'm going to write that straight out. I'm just going to copy that up here. Okay, and likewise on the left hand side, I have to multiply this by this. I'll write that out. There. And this is the result I'm going after. Let's look at this and think about it a bit. Now on this side here, on one side, I have the coordinates in a certain frame of reference. Let's say that's the frame R with coordinates x and y and so on, without the primes. And that one is in another frame of reference. Call it R primed with the primed coordinates. So in this frame, I have these vectors, like say 2 points. So each vector there represents a point on the coordinate, like that might be x1, that might correspond to x2, y2, z2, and so on. Okay. Okay, so those are that coordinates. And when each of this point or the vector in this frame is transformed to that frame, it takes on different values with respect to that frame. So that might be x2 prime, and that might be x1 prime. Okay? And the relative positions might also be different because of, say, length contraction and time dilation. So we expect different values for those coordinates. So I transform two of these vectors from one frame to the other frame. Right? So all the coordinates are going to be different. But what this equation tells us is that there is one thing that has not changed. And that thing is the number that we would get if we multiply those two vectors like that. You see, if I have the coordinates for those 2 points, here and here, and if I multiply them in this way, I'll get an answer. Alright. Now if I go to this other frame, if I have those 2 points with those coordinates and I multiply in exactly the same format, and I get an answer, now that answer must be equal to what I got before I do the transformation. That's what the equal there means. So we have something which doesn't change when we do the Lorentz transformation. And this property and this format of the multiplication becomes something quite useful in special relativistic calculations. So because of this, we describe it with some terms. All right. This way of multiplying the two vectors, it is called an inner product. So we describe this by saying that the inner product is invariant under a Lorentz transformation. Or we could also say that the inner product is Lorentz invariant. And if we say that in just 4 words, 3 or 4 words, this is what we mean. Alright, all those that I've described in the past 5 minutes, that's what we would mean. Now if you just a point about the actual calculation itself, if you look at those two vectors, now if let's say you ignore the CT there and the CT there, alright? If you ignore those two terms and just look at the x, y, z and the x, y, z, you would be just looking at the dot product in 3 dimensions if the CT is not there. But now that we have included the CT, alright, the actual calculation is not so different from doing a dot product. I mean, it would be almost as if you are doing a dot product with vectors that have 4 coordinates. Except that for the CT term, you must have a minus sign. Right? You must insert a minus sign there. So you can still do the calculations as if you have done, as if you are doing the normal dot product calculation. And there is another term that we need to learn. And that term is called a 4 vector. And 4 vector is a name given to this vector. So you have the x, y, z and you have a CT down there. We call that a 4 vector. Another way to write it is with the number 4, so just 4 vector. And we will put a hyphen in between to make it into a single word. Okay? Now, and just to make things easier to talk about, we are more familiar with the coordinates x, y, and z in 3 dimensions, and for these familiar vectors, we will call them 3 vectors. So that would be a 3 vector. Now, and there is a definition for 4 vector. A 4 vector can be any vector that transforms according to the Lorentz transformation. Now that is a rather abstract statement to take in. What it means is that if you look at these 4 coordinates, which I call a 4 vector, you know that physically these refer to, say, a point and a time in a particular frame of reference. And if we take this 4 number and we say that we transform it using the Lorentz transformation, what we mean is that we go to another frame of reference which is moving at a certain velocity with respect to this one, and we calculate what the time and positions are from the point of view of that other frame of reference. So this means Lorentz transformation. Okay, and when you say it transforms as the Lorentz transformation, what it means is that if you use the Lorentz equation to calculate the new coordinates, you will get the correct answer. That's basically what we mean when we say transform according to Lorentz transformation. Now, and we understand that this is the case for x, y, z, and t. That's just the position in space and the time. Now, but if I'm going to make up a name for a 4 vector, surely it's only useful if there are also other types of vectors that have this property. And in fact, there are 4 vectors for not just for position. There is also 4 vectors for velocity, for force, for momentum, and so on and so on. Now, to understand it better, it would be useful to look at some examples. Right, but we shall do that in the next session. So we'll stop this session for now.